In this video, we are going to look at molecular polarity. And typically when we're looking at molecular polarity, we're looking at covalent bonds, right? So we're looking at bonds in which atoms will share electrons. Now, there are two types of covalent bonds. There is the nonpolar covalent bond, and there is the polar covalent bond. And more specifically, we're going to kind of look at a little bit of both. Primarily, we're going to look at polar covalent bonds. Now, when dealing with polar covalent bonds, or dealing with covalent bonds in general, where you're trying to find the polarity of the molecule, it is important to pretty much be able to look at the periodic table and find numbers that refer to the electronegativity. And I've spoken about this in a previous video, but we're just going to look at polar molecules with regards to this video, which kind of steers a little bit in a different direction from what I've already created. Now, when we're talking about like electronegativity, we're really looking at how strongly an atom will actually hold on, let's say, to an electron, right? So if we had something like with two atoms, right, that are sharing electrons. So let's take, for example, something like carbon. We know carbon will share with something like hydrogen. So that sharing of the electrons, right? If we are able to find this electronegativity, or should we say the change in electronegativity, right? Where we find the electronegativity number of, let's say, one of them, we subtracted by the electronegativity of the second one, and we end up finding out really within what range. And we're not going to really worry about the range because that was in my previous video. But what we're looking at is really which of these atoms in this bond, right, is carbon or is hydrogen higher in terms of their electronegativity. And typically, the higher of the two numbers means that atom will it'll share the electrons, but it's kind of like, well, let me share them, but I want them more on my side. As opposed to, okay, you've got your electron, I've got my electron, and let's share them evenly. Now, probably this carbon and hydrogen isn't really the best example, because a carbon-hydrogen is typically considered a non-polar covalent bond. But let's look at ones that actually are here. So let me pick a different color here. So something like carbon double bonded to oxygen. Right? So what we have here is we have a polar covalent bond that occurs. Right? And again, refer to my other video when talking about changes in electronegativity regarding identifying these polar covalent bonds. But what we have is a polar covalent bond. And if we were to look at the electronegativity, oxygen, right? Oxygen has the higher electronegativity number, and to know that it's not, I don't think is a wise choice to have to memorize this from the periodic table. You can find this on a periodic table. So when you have something that is considered covalent, right? Any polar bond, any polar covalent bond, right, have what we call bond dipoles. And let me write that word down here. So they have something called bond dipoles. Right? So think of it this way. Poles, we know, think of like north-south, right? But in essence, what we're referring to with poles, we're talking about positive and negative poles. Di meaning two, so we have two poles, one being positive, one being negative. Now, how can I identify between carbon and oxygen which will be slightly positive, slightly negative? We've already identified this. We've identified that it's a polar covalent bond, meaning they're sharing these electrons. However, there is an unequal sharing. Now, who's the one kind of hogging that shared electron. Let's look at who that is. And by looking at it, you're going to find out that, as we said, oxygen has the higher electronegativity number between oxygen and carbon, which means oxygen is going to pull those shared electrons from carbon a little bit more towards it, right? Towards more its region, its cloud region of electrons. So what we can say now about something that is considered a polar covalent bond is it has these bond dipoles, and because it is slightly negative, right? So we're going to say it's slightly negative, but we're going to use this symbol here, right? So this symbol means that there is a means that there is a partial, right? Partial negative charge. Why? Because the electrons are being pulled over towards oxygen, which means if we have one pole that is slightly negative, which is the oxygen, that means the other pole has to be slightly positive. So we end up drawing that, and what we're going to end up doing is with this pole, let me just erase some of this here, is we're going to eventually create pretty much what we call a dipole vector point. And this dipole, right, dipole vector, this is supposed to be a C vector point, is really an arrow that shows the direction of this polarity. And this polarity always goes from a positive end to the negative end. So how are we going to draw this dipole vector? And the direction is, as we said, it goes from positive, right? So it goes from positive all the way to negative. Notice what I did? I ended up drawing like a plus symbol, but instead of just stopping at the plus, I continued it with an arrow in the direction of the negative pole, right? And this is really how you show what we call pretty much polar covalent compounds. And in fact, this is really what you're showing in terms of the polarity. So you're going to show this, right? This is our dipole vector point. This actually shows the polarity of an actual bond, right? So other examples with regards to other typical polar covalent compounds, pretty much anytime we see carbon and oxygen, right? So look for things like carbon and oxygen, look for things like nitrogen and hydrogen, look for things like oxygen and hydrogen. So if you see these three bonds, of course there are many more, right? We've got other things like, what other ones that I can think of right now off the top of my head? Carbon, nitrogen, right? So if we see bonds like this, maybe carbon and fluorine, right? These are all considered polar covalent, right? So when we see this, we don't really even need to worry about finding the change in electronegativity to identify. We can almost tell, right? Things that are considered non-polar, right? As I've pointed out already, pretty much carbon and hydrogen is considered non-polar. And so with things like carbon and hydrogen that are non-polar, we do not draw these dipole vector points, right? Because there is no, even though there is, there is still a slight pulling of electrons, but it's so minimal that it's not referred to as a polar covalent bonds. Now, things to keep note of is that even though we have, right, a polar covalent bond, right? So just because some molecules are polar covalent, right, doesn't mean that it is a polar molecule. So not all, right, not all polar, right, covalent bonds equal polar molecules, right? So we might have a polar bond within a molecule, right? However, we don't have what we call a polar molecule, right? So let's take, for example, something like here we've got carbon dioxide. So carbon double bonded to oxygen, right? So we know that as we've referred to before, right, here the bond between carbon and oxygen, as we said, it is polar, yes, right? So, and we know that oxygen is slightly negative. So what happens is, let's label that. So we said that oxygen is slightly negative, carbon is slightly positive, which means between now the bond here goes the same way, right? This side is slightly negative with the carbon being slightly positive, right? So when we have something like that, right, we still have these polar bonds, but however, look at this now. I'm going to draw this that plus symbol, right? So remember, we're going to draw that dipole vector, right? So we've got it's plus and then the direction of the negative. However, that direction of the negative goes also in the opposite direction, right? So pretty much what happens is this kind of polarity, they counteract one another, right? So what we have is we've got equal bond dipoles, but they're acting, right, pretty much in an opposite direction, right? Opposite direction to one another, right? So they're pulling away from one another. So because carbon, even though this between this carbon and this oxygen, it's it's polar, between this same carbon and the other oxygen is still polar, because they are that negative is pulling in opposite directions. They are counteracting one another. This compound here of carbon dioxide, right, is considered a non-polar molecule, right? It has polar bonds, don't get me wrong, right? We've got polar bonds here, right? However, in all, it is considered still a non-polar molecule because this polarity is actually counteracting one another. It's acting in an opposite direction to one another, right? So what's another example? Well, we have something like, I'm trying to think of one right now. So let's look at something like carbon tetrachloride. So the bond between carbon and chlorine is considered also, right? So if we look at one of these, right, we know that the carbon is slightly positive and the chlorine is slightly negative, right? So what happens here is we've got chlorine has the higher En number. So that means chlorine is slightly negative and all of them slightly negative, right? Which means carbon is slightly positive. So in such the polar vector is going from positive to the negative. So they're going apart from that central atom. So they're counteracting one another. They're going in, as we said before, opposite directions. So even though the bond between carbon and chlorine is considered a polar bond, right? Carbon tetrachloride is really considered a non-polar molecule because the polarity is going in opposite directions. All right, so let's look at ones that are considered. So let's look at the ever famous water molecule. All right. So the oxygen here is really the slightly negative, the hydrogen being slightly positive, right? And now notice the direction in which it's going, and really it's going from positive to the negative, right? From positive to the negative. So it's going really from the bottom here, where the hydrogens are, to the top. So we don't draw it, we can draw it that way, or we can draw it that it's going from positive here to the negative, being the oxygen up at the top. So because the bond dipoles, they don't counteract one another, right? They're going pretty much in one direction, right? So they're going in one direction. We have polar bonds, but here we have polar bonds that also refer to a polar molecule. So we have here polar molecule because they're going in that one direction. Let's draw one more example. Right, we're going to draw something like chloroform. Right, so carbon, hydrogen, chlorine, chlorine, chlorine. And now this is a slightly different. This is slightly different, right? Because here, even though, as we said before, this being slightly positive, the chlorines being slightly negative, right? Going from positive to negative, right? Positive to negative, positive to negative. So it's going in really in one direction, kind of from one to the other. So just like we drew with oxygen and hydrogen in water, it's going from the positive carbon to the outward negative chlorine. So the bond between carbon and chlorine, as we said, is considered polar. Between carbon and hydrogen is nonpolar. However, it is still referred to as a polar molecule. So let's kind of recap. Let's recap all this. So few things to make note of. All right. So the first thing, if the molecule really has no polar bonds, right? So we've got no polar bonds, right? Obviously, nonpolar molecule, right? That's a given. All right. Typical nonpolar molecules, pretty much any of the. So we have something like here, right? Something like butane here, right? All nothing but carbon-hydrogen bonds. So we know we have a non-polar molecule. Now, if a molecule contains at least one, right? It contains at least one polar bond, right? One polar bond, not like not like the carbon dioxide, right? The carbon dioxide had two polar bonds, right? Talking about one polar bond. So if we have like one polar bond, obviously the molecule is considered a polar molecule. Here's an example of one, right? So let me draw one here. So we're gonna have something like carbon, right, bonded to a single chlorine, but bonded to three hydrogens. As we said before, the carbon is slightly positive, the chlorine is slightly negative, so the polarity is going from positive to negative. So we have one polar bond. These are non-polar, but this whole molecule, because it's going in one direction, the polarity, right? They're not counteracting with one another. It is referred to as a polar molecule. And our last point, right, our third point here to point out, or really, well, it's a two-parter, right? So if a molecule contains bond dipoles that do not counteract, right? So if it contains polar bonds that do not counteract one another, right? So they don't go in opposite directions, right? This is if you've got, right? This is if you've got more than one polar bond, right? You've got 2 or 3, like I showed you before, right? This one only had 1. So our step 2, if we're referring to having at least one polar bond, a molecule is considered polar. However, if they contain more than one and they don't counteract one another, right, we are referring to a polar molecule, right? And this example pretty much just like the ones we did before, right? Like water. What was the other one that we did? We had the chloroform, right? Now, and our fourth point, right? What happens if we have, right? Oops, I almost forgot how to do it in Roman numerals. So even if we have polar bonds, right, more than one polar bonds, right, that go in opposite directions, right, that counteract, right, one another. All right, and this example pretty much like the one I showed you earlier, right, with the carbon dioxide. The other one was the carbon tetrachloride, right? If they counteract, right, these pretty much are, these molecules are really, even though they have polar bonds, they are really considered non-polar molecules.